So yeah, my name's Dr Eamon Scullion. I'm an associate professor in mathematics at Northumbria University in Newcastle. And my primary area of research is into the surface details of the sun. So I'm mostly interested in looking at what is going on at the surface of the sun. And the way I do that is by using really high resolution observations of the sun taken from telescopes located in the Canary Islands. So the telescope that I'm most familiar with is known as the Swedish 1 meter telescope. And it's based in the island of La Palma in the Canaries. And I've been working with observations with that telescope for the last 10 years or so. And yeah, we've done a lot of exciting science with that. But the next big thing is going to be the Inouye Solar Telescope. The first light images have been really exciting for me to get an even more detailed insight into what's going on at the surface of the sun.
Yeah, it's interesting just kind of talking about the Inouye telescope. I mean, how did the project come together? And I suppose most specifically, how did you and your colleagues at Northumbria get involved in the project?
So the project itself was originally conceived already 15 to 20 years ago in the US at the National Solar Observatory in Colorado. And astronomers who observed the sun came together and decided that we needed to really take the telescope technology to the next level. So at the moment, there's a range of classes of telescope from 1 meters to about 1.5 meters in terms of their aperture diameters. And those telescopes can only tell you so much because they're as big as they are. But the decision was taken, right, we need to go to the next level, and we're going to build a 4 meter class telescope. So this is a substantial scale up in terms of the size of the telescope, the telescope mount and the telescope assembly, which came with its own challenges. If you focus light, if you've ever put a magnifying glass, light through a magnifying glass, you'll see that it quickly focuses the light and it can build up a lot of heat. And so there was a lot of engineering challenges and technical challenges with that. So for the last 15 to 20 years, this telescope has been under construction, mostly during the last 10 years. And the UK involvement in this is that we are a consortium of universities led by Queen's University in Belfast, and Northumbria University are part of that consortium of 8 different universities. And about 6 or 7 years ago, a bid was put forward to our research council that fund the research that we do, the STFC, the Science and Technology Facilities Council, in order to get involved in this project and support the US effort to get this telescope up and running. So the UK contribution has been through an industrial partner called Andor Technologies. And they're an Oxford Instruments-based company, and they basically have redesigned or reinvented how we take high-resolution, high-cadence, so very high frame rate images with very, very high large format CCDs. So Andor have partnered with a group of us as university solar physicists, and we got together and got support funding from STFC to the value of about $2 million. Or £2 million, sorry. And that money was used to build and to test and design new detectors for imaging the sun, to be able to take the light from the telescope in America at the Inouye Solar Telescope, to take all of its light and to capture images at a very, very high frame rate in order for us to be able to see, in order for us to be able to detect the subtle changes that happen right at the surface of the sun. So our involvement has been to provide the detectors that are being used to record the images coming from DKIST or from the telescope in Hawaii. And since then, we've been actively involved with Andor in supporting them to outline what requirements, what are the specifications that we require for these detectors, how should they perform. And we've also been involved with the development of data pipelines. So when the telescopes start receiving light, we want to be able to interpret those images using software, using computational modeling, to be able to understand the physics of what those images are telling us about what's happening at the surface of the sun. So we've been developing the data analysis software in order to be able to be ready for whenever the data comes online and we can start interpreting it, and we'll start to get some unique physics out of that. So aside from helping to get the detectors there and up and working at the telescope, we've been working on the software development behind the data analysis that's going to start coming out whenever the data becomes available to us.
What sort of features on the sun can the telescope see, and kind of like how, I suppose, unprecedented is it? Is it like it kind of see things that other telescopes have never been able to see before?
It's a new window on the sun. It's a window that we have never observed before. It's a window that will allow us to see details that we just were not capable of seeing before. So currently, with the current ground-based telescopes, and there's a whole host of space-based telescopes as well that NASA and ESA have put up in orbit for looking at the sun. But the ground-based telescopes are at a unique advantage over those because they have, larger. They're larger telescopes and they have larger apertures, so they collect more light, and we can focus more into the details of the surface of the sun. And so, because the telescope is a 4-meter class telescope, it means that we're able to get right down to very high resolution images to be able to look at these minute changes that happen on very small scales on the surface. And to sort of put it in context a bit, we're going to be able to observe structures that are at least 5 times more resolved than what we've been capable of doing so far with even the best telescopes that we've got currently. So we're going to have a step change in our ability to identify and to track and to understand subtle changes happening at the surface on a very small scale. And we want to do that because that's where the magic is. That's the devil is in the detail when it comes to solar physics. And all of the interesting physics happens on scales that we have been unable to observe. Very, very small scales on a very rapid time scale as well. So we want to see those subtle details, and that will hopefully allow us to verify the models that we've got to help us understand the physics of the solar atmosphere, the atmosphere above the surface of the sun.
You actually kind of answered one of my next questions, which was going to be, if we have missions like the Solar Orbiter and the Parker Solar Probe, which are kind of spacecraft that are going to study the sun up close, what's the need for a ground-based telescope? But I suppose you've just answered that. It's all to do with aperture, really, isn't it?
It's all to do with the size of the telescope. Yeah, the bigger, the better, and the more detail you can expect to get. So, with Parker Solar Probe and with Solar Orbiter, which just got launched the other week, they have their unique advantages that ground-based telescopes do not have. So with Parker Solar Probe, we've got a small satellite that's in orbit around the sun, so it's allowing us to have different perspectives of the sun away from the view that we've got from Earth. But it's also actually going to measure properties of the solar corona, this atmosphere above the sun. It's going to look at the properties of the corona in what we refer to as in situ. So it's going to measure physical properties about the corona locally as the satellite passes through the corona. So those are the most direct measurements that we can expect to ever get. Whereas with the ground-based telescopes, we're essentially having to interpret what we see. We don't get to go there and to actually measure the properties locally. So having the satellites is giving us a huge vantage point because it's allowing us to look at the physics locally in a very small, even on a very subtle way as the satellite passes through the corona itself. Solar Orbiter is going to be the first solar satellite to actually image the poles of the sun. So we've had satellites that have flown over the North and South Pole, but we haven't had direct images of the poles. So that will be a unique vantage point as well. And the other big advantage of going to space is that you get to look at the sun in different shorter wavelength ranges. So in the X-ray range and the extreme ultraviolet, which gives us another insight into the physics of what's going on. The big advantage with the ground-based telescopes is that you get bigger telescopes, so you see more detail. And as I say, the devil is in the detail, the physics is in the detail, the instabilities that are present in the sun are apparent to us, and we can see how flows evolve relative to each other and how different eruptions from the sun are triggered, and the dynamics that lead to those eruptions in the sun. We can see the details, and it's the details which is where the magic lies. And the other big advantage is that with ground-based telescopes, you can walk up to the telescope and just take out the instrument and plug in a new instrument, and you don't have that. You have that continual regeneration of new instruments with the latest, newest technologies. So we can continually upgrade the Inouye Solar Telescope over the next few years. And that will enable us to be able to do our analysis and to understand the physics from slightly different perspectives at different wavelength ranges and with different instrumental capabilities. So there's going to continually be an evolution in the ground-based telescopes, which is something you can't do with space-based telescopes because you have to go to space to replace them, and we don't do that currently. So it's a really exciting time, and solar physics is really going through a golden era right now, because we've had so many new satellites being put up, and with this huge development of the ground-based telescopes, we're getting a completely newer and richer perspective of what's going on the sun.
I think it's definitely worth talking about the first light images that were released from the Inouye telescope, because they kind of showed this almost like cracked surface of the sun. I mean, just exactly what were they showing, and could you talk us through a bit kind of about the science that's kind of been discovered as a result of those?
Yeah, so I've got the blow up image here of the sun, of the first light images taken by the National Science Foundation Inouye Solar Telescope. So this is part of the field of view of the first light image itself. And when we look at the image at this resolution, we can see already, even though it's one instant in time, we can already identify features that are more detailed than what we understood about them before. We can identify structure that implies a physical phenomenon is taking place there. So even in one snapshot, we can interpret some physical processes going on here. So what generally what you see here is this network of, as you say, cracks and these giant kind of what look like sort of a bubble network of structure kind of throughout the whole image. So we see these sort of bright bubble-like structures and these dark kind of fractured lanes that kind of exist between the bubbles. And what these are in fact bubbles, and bubbles of hot plasma. So this is very similar to what you get if you're boiling an egg in a saucepan. You're going to see lots of convection in the water as the water gets heated up. So you get bubbles rising to the surface, and you see the bubbles appear here as bright features, and that's because they're hot. So the hot plasma rises to the surface, and we see them as brighter features. And then the bright bubbles, essentially, all that hot plasma moves away from the center of the bubbles, and it cools down. And when it cools down, it becomes slightly more dense. And it becomes slightly more dense, then it sinks back into the sun. So you have this sort of cycling going on of hot plasma rising up in the center of the bubble. It appears very bright. And then it moves to the edges and it appears darker because it gets denser, and it's relatively cooler, and it sinks backwards. So all of these cracked lanes are basically fractures in this bubble network. And that's where we see sinking cool material. But what's also apparent about this image is that we have these particularly discrete, these particularly apparent brighter features, these little bright, what we call bright points. So they're very discrete, well-defined features with very clearly defined edges. And what we knew about, we didn't know very much about these before. We knew that these bright features are actually unique locations here, because that's where magnetic field concentrates much more strongly. So if you imagine a distribution of positive and negative polarities of magnetic fields here, then we know that where we have bright features, like just along here, for example, that's where magnetic field is particularly more bunched together, more concentrated. And what happens when the fields become more concentrated is that they evacuate the plasma. They push the fluid away from that location. And that enables us to look a little bit deeper. So when you have brighter features, what it implies is that because the fluid is evacuated there, we're able to observe deeper. It's like a hole kind of in the surface. And because we can look deeper, then we get back down to the even hotter plasma. So it appears ultimately brighter again. So we're looking a little bit deeper, it's a little bit hotter, and therefore it's a little bit brighter than everything else. But that's where we have these concentrations of magnetic field. These are, if you like, the portals through which energy gets transported away from the surface out into the atmosphere above. These are the channels through which energy gets delivered out into what we call the outer solar corona. And the big question in solar physics that we want to answer here is, how does that energy get transported outwards? So what this image is able to tell us is that there is a lot of structure in these bright points. That we see these little, what we call, some people refer to these little bright patterns, these kind of little ripple effects, these little ripples that you see on the edges of the bright points. Some people refer to those things as crinkles, almost like curtains in the structure. So we see these folds everywhere here. You can see them along here as well. This little ripple effect here, down here. And what we haven't been able to see that before. Before, when you looked at an image like this with the telescopes that are currently operating, this was just a bright blob. But what we see now is a lot of detail and a lot of variation of intensity and structure across these bright points. And we want to understand what is going on there. We want to understand, how do these ripples evolve in time? Do these bright points become more twisted in time? Do they begin to spiral? We see some sort of hints of twisting and spiraling of the structures down here, for example. But we need to see the image sequence to be able to determine how are these things evolving. But one thing that I'm particularly interested in is a phenomenon which I was part of a discovery paper in 2012 that was published in Nature, the Nature journal. And that discovery paper reported the idea that possibly these magnetic concentrations are becoming twisted by vortex flows. So I was part of a discovery paper on what we coined the magnetic tornado. So a magnetic tornado is a vortex of magnetic field in these bright points. And what we think is those magnetic tornadoes twist up the fields. And as they do that, they launch lots of different, what we call magnetohydrodynamic waves. And energy gets transported in these waves out to the corona above. So I'm particularly excited about this image because I can see signatures of twisting and writhing of the structure. And I think that when we look at these and we look at the time series of these, we're going to be able to see evidence of this magnetic tornado phenomenon that may be at the heart of how energy gets transported out into the corona and enable us to understand the origins of the heating of the atmosphere of the sun itself. And it's just one image. And over the next 5 years, this telescope is going to produce more images and more data than we've ever recorded from the sun ever since the first observations were taken by Galileo back in the 17th century. So in the first 5 years, this is going to give us a ton of information and a ton of insight into really the heart of how energy gets transported out from the surface to the atmosphere above.
Fantastic. Why do you think it's important to to study the sun and solar science, and also how can it kind of help protect Earth, because the kind of activity of the sun has an effect on life on Earth, doesn't it?
Yeah, so the sun is the giver of life on Earth. Without sunlight, we would not have any photosynthesis, we wouldn't have any generation of energy through vegetation, and life would probably not exist on Earth. And so the sun is fundamental in that sense to life on Earth. But the sun has much more impact on our daily lives than we might otherwise expect. And this happens when large explosions happen on the surface of the sun, which we call a solar flare. And so when large explosions happen on the surface of the sun, often you get the eruption of what we call a coronal mass ejection. A piece of the corona literally gets ripped out from the sun and fired off towards the Earth. And as that bubble of high energy radiation and plasma and gas and magnetic field, as that twisted, hot, energetic bubble gets fired towards the Earth at about the speed of a bullet, it impacts upon the Earth's magnetic field, and that impact has a kind of a collisional effect. And that collision launches or releases billions of tons of high energy particles into the Earth itself. So there's a kind of sequence of events that happen as energy leaves the sun and hits the Earth and gets transported through the Earth, and it leads to currents flowing through the Earth's surface. So there's a lot of evidence, even recently, about what is the impact. And Lloyd's of London published an article in 2013 that reported on the potential cost of a super solar flare, a superstorm, and how that would what causes that would have on the Earth today. So because we have so much more reliance on technology, we need mobile phones, we need GPS. All of that technology relies on satellites, and satellites are particularly vulnerable to these solar flares because satellites don't like high energy particles smashing into them during these solar flares. So during a solar storm, satellites can experience radio blackout. We lose communication with the satellite temporarily, and therefore we lose radio communication across the world, and that can have massive implications for global trade. For example, it can have implications for the power grid. For example, in 1989 in Quebec, there was a blackout that caused a complete shutdown of the power grid across a large part of Quebec in Canada within about 9 seconds. And it took many hours for them to get that system back up and running. And they calculated that the cost to the local economy or to restore the power grid system was on the order of about 2 billion Canadian dollars. And so the potential economic impact is real. And there's a lot of other influences. For example, because of these high energy particles coming in to the Earth from these interactions with the Earth's magnetic field, they tend to concentrate around the poles of the Earth. So you get this influx of particles towards the poles. That leads to what we know as the Northern Light phenomena. We can see Northern Lights when we go to Scandinavia, but those high energy particles actually increase the radiation level in the upper atmosphere to quite a large extent. So what airlines do is whenever solar storms take place, the airlines will reroute flights away from the North and South Pole. And so transoceanic flights would typically get rerouted. And there was a particularly bad solar storm during the Halloween of 2003, in which 6 major airlines had to reroute flights, and they had to ground flights in Canada because of the increased radiation levels that occurred during the solar storm, particularly in the ionosphere. So there's quite a lot of evidence of the potential impact on transportation and the electrical power grids, which can affect people's lives in a very real way. So it's important to know when these events are going to happen. And in order to know when the events are going to happen, we need to be able to predict them. So tracking large eruptive phenomena on the sun and looking at the changes of activity in high resolution before the storm is triggered will be able to enable us to say, right, we understand the physics of what's going on. We understand when, potentially, we can understand roughly when this thing's going to occur. And at that point, we can already take preemptive steps to inform communications, those people involved within communication systems globally. And for example, the UK Met Office has a space weather prediction centre, so they're interested in providing forecasts for other governmental bodies that would otherwise be affected by large radio blackouts. So this is a very real phenomenon that the government take very seriously, and we need to be prepared for that. So solar physicists are working to determine accurately when this solar storm is going to come, and in order to do that, we need to be able to look at the details of the sun in a very accurate way, and track how they change in order to make accurate prediction.
Fantastic. Well, Eamon, thanks very much for speaking to me today. It's really interesting, and I suppose we'll look forward to more science and images coming up from the Inouye Telescope. But yeah, I just want to say thanks for joining me today and telling us all about the secrets of the sun.
Great. Thank you for having me.